8 or 9 anesthetics, because I guess I metabolized it quickly and it was using a fast-acting one. So 8 or 9 shots. I'm still numb. I have no idea if I have an accent or a stutter or something right now. I do, I apologize. So you guys have been very patient with me, because the last time we were together I was writing a grant in the middle of all this. You guys put up with that. I really appreciate you putting up with me. I'm not, this life for me is not this bad, usually. Also, since we're doing a mea culpa here, the last time we were together was a month ago, and I don't remember what I taught you, so I expect that you probably don't remember a lot either, and I'm fine with that. I checked the schedule quickly last night, and I think you've had one other BAH class since me, the cytokine class. So if you'd like to answer some questions about cytokines before we go on, I'm more than willing to do so. Otherwise, I put in 3 or 4 slides of reminders of where we were, because I don't expect you to remember. And cut Frank breath too. So any questions about the cytokine class, just so I can be on the same page as you guys? Sure.
I'm still not completely clear on the differentiation between a cytokine and a prostaglandin.
Okay, actually, I am going to be talking about prostaglandins today, so I will clarify that. And it actually, some of the things I'm going to do today fit into that question, so that'll work out fine. But the short answer, just so you know, the short answer is the cytokine is a protein. Prostaglandin is a product of arachidonic acid. You'll see that in a moment. They are both released at sites of inflammation. They're both involved in communication among cells. Cytokines are more, the communication, the messages carried are far more complex than a prostaglandin. Prostaglandins give a warning that something's wrong. Cytokines provide a fair amount of information when they engage with their receptor. Yes?
Is this PowerPoint on Canvas?
Excuse me?
Yes. Which one is it? Refresh the page.
I'm sorry, I didn't catch the question.
Is this on Canvas? Sorry. This PowerPoint, is this on Canvas?
We have the access to it.
I mailed it to a woman named Heather.
It's on this
Ramsey.
It's where?
It's on the survival guide.
We have this one still. It will make it work.
So I mailed it to a woman named Heather Ramsey. I will mail it to her the moment the class is over. You didn't get it? It's not posted?
We have
I'm sorry. I don't know who Heather Ramsey is, but... Okay, yes, so I apologize for that. Any other questions? All right, so let's remind you what we talked about last time. And remember, anything in red is going to be on the exam. It's going to be the question. It's going to be word for word. The immune system does this, this, and this, and protective and repair will be on the exam. When we talk about the immune system, and by the way, we were told there's a change in schedule also, or a change in syllabus, not the time. They left out, when I got the syllabus in December, I'll be honest with you, I didn't look at it too closely. And when I started preparing, because you've got a lot of me this week and next week and the week after, started preparing for the next 2 or 3 weeks, I noticed the most important class wasn't even listed. So I protested over the weekend, and they've taken away one of my classes, which makes no sense to me either, and substituted it with an important class, but now you're not going to get the other class. Sorry about that. I should have called it in December. Okay, but a key, you're going to hear from me for the next 2 or 3 weeks now a lot about cells and proteins and enzymatic reactions that are critical for host defense. And I just want to emphasize, and I think I have probably 2 or 3 slides that say that we cannot forget skin, mucus, saliva, peristalsis. Remember, I use the expression port of entry with you guys. The main sources of infection is not when you cut yourself, which does happen. It is through entry of organisms through holes in your body, and those holes are covered with mucus, saliva, peristalsis, if you're poofing, coughing, the whole. Those are incredibly important lines of defense, and I don't want to minimize them. They're not particularly taught. I don't know what else to teach about coughing, but you cough. But please don't forget them. They're very, very important. 2 branches of the immune system are innate and adaptive. Today's class is about the innate response. The innate response is pattern-based. I can't remember, we talked about patterns last time, but we'll do it again just to remind you and to remind me that you should do it. Innate is usually considered the first response, the early response, and we'll focus on that today. Mostly phagocytic cells, neutrophil is the main cell, macrophage is the second phagocytic cell, and they contain granules. The other half of the immune response is the adaptive response. We'll get to that, not Wednesday, but I believe Monday of next week. And the key words, they will be on the exam. Adaptive response is defined by its specificity, its diversity, its memory. We talked about memory last time. Vaccines, the fact that you don't get chickenpox twice, that kind of stuff. Specificity and diversity, we'll get into a little bit of specificity today. Diversity we'll get into in about 4 or 5 classes, and I'll warn you before we get into it to hold your seat, hold tight, tighten your seatbelts because it's going to be a tough class. I'll try to simplify it as much as I can, but it's an incredibly complex molecular biology, try my best. Innate and adaptive immune responses talk to each other. They talk to each other by this cell called the antigen-presenting cell. I described the antigen-presenting cells last time we were together. But you remember, did I do the bowling ball, the 2 big toes business with you guys?
Yes.
Okay, so we'll go back. We'll use that one again. Remember, you step on a rusty nail with your left big toe. You drop a bowling ball on your right big toe. We're going to deal with the responses that occur during those next minutes, seconds, minutes, and hours. Seconds will be production of prostaglandin. Minutes will be something you don't know yet. And then hours will be the introduction of neutrophils into those 2 big toes to deal with the mess that was created. We'll deal with all that today. White blood and antigen-presenting cells are in the big toe. If the neutrophils and the macrophages deal with the problem's gone. 2 days later, your inflammation is gone, everything's cool. If they don't deal with it, antigen-presenting cells leave the big toe, go to a draining lymph node, in this case behind the knee, but the draining lymph node, wherever it may be, and present, truly just present. Display on their surface the antigen, the foreign protein, such that the T cells in the lymph nodes are able to respond. It's that antigen presentation T cell activation class that was left out, which when I saw it was left out, I insisted it be returned, and it is now. Thymus, I'm not going to talk about what goes on in the thymus. Another faculty member, actually the person I found out who directs this course, I found out over the weekend, was bitching and moaning. You like that, huh?
That is ground zero what happens in academia, but it's so rare that someone's honest about it. It refreshes my soul.
The thymus is, T cells go from the bone marrow to the thymus where they get educated. I believe the director of the course, Dr. Pandiyan, I didn't get that right, will be teaching about thymic education. If she doesn't, I've already talked to your president. Yes, I already talked to the president of your class. I'm more than willing to give 1 review, 2 reviews, 10 reviews, whatever you guys want to make sure you get it. And I'll review my stuff and anything you got wrong. And then lymph nodes are where the antigen, not today, but the antigen presenting cell goes to the lymph node, talks to the T cell, and gets the adaptive immune response going. All of this should be reviewed, but I appreciate it being not. I probably, you know what, I don't know why I put this in. I was wrestling with putting this in last night, and I said, no, don't put it in. So we're going to avoid it by not. Do it spending time with it. Okay, so this slide and the next slide, and maybe even a hidden slide, which you don't have obviously, emphasizes the difference between an innate and adaptive. Rather, I'll put this one up because it's easier to read. Is there any confusion in your mind right now of the difference between an innate and adaptive response? We'll go, the next hour and 20 minutes we're together is the innate response, and then we begin, well, Wednesday is innate also, and then Monday we begin adaptive. So you'll get this again. But if there's anything you don't understand, just shout it out now. Sorry.
Is the relative memories of each?
There's no memory in innate.
Okay.
Well, I told you about my 95-5 rule. So I am only going to tell you 95% of the truth. There's 5% that is either current literature or so freaking complex that it's just not something I have decided that you shouldn't be bothered with the first time you're being introduced to the field. So there's 5%. In the 5% world, there is some memory in innate. But for today, no memory in innate. Memory goes with adaptive. For your exam, memory adaptive. Yeah.
So the body creates antibodies to chickenpox, but
That's adaptive.
But then shingles shows up later. So,
Right.
So maybe the memory doesn't always work.
It doesn't work.
Okay.
It absolutely doesn't work. Why do you, the rule is you get a tetanus vaccine, you should get a booster of a tetanus vaccine every 5 years or 10 years.
Understood.
Why? If memory works, you don't need the booster. I mean, I just got 10 shots. I'm going to Africa, I got more shots than I had arms for. And some of them I have to get boosters in 6 months after I return from Africa. So memory is not perfect. And nothing in biology is perfect. And that's sort of part of my 95-5 rule. I'm going to give you the 95 so you get it. Will you run into inflammation in your careers? Absolutely. A lot. But you don't need to know, please, I hope you don't consider what I'm about to say condescending. But I don't think you need to understand inflammation at the same level I do.
Right.
Because your introduction to it will be, one, more clinical than what I do, and two, never at the depth of what I think I know. I don't know if I know anything, but what I believe I know. And that's why I'm hiding things from you. I hope you're not offended by that. If you are, talk to me offline.
Quick question.
No, I'll listen. I wasn't being sarcastic. I'll listen.
The second point expressed by all cells of a particular type. Can you refresh which cells in particular?
Yes, so we'll actually do that in class. So since today is all about the left-hand side, the innate side, all the yeses we're going to deal with today. Okay, I remember I mentioned I thought I had 2 slides about emphasizing skin and mucus and all that, and you'll notice that the emphasis on this slide for an innate response is all ports of entry, all the holes in your body, because that's really where most infections occur. The oral cavity being obviously the beginning of the GI tract, which ends, you all know where it ends. We have a lot of enzymes that are involved in maintaining the biology of the organ, and some of those enzymes are rather aggressive: proteases, nucleases, lipidases, sucrases, things that digest carbohydrates. And all of these molecules, DNA, protein, lipid, are also made in infectious agents, so therefore we are attacking the infectious agent with a series of enzymes. And that's what this slide is all about. You do not need to know anything on this slide. For me, for the exam. I mean, I hate to keep coming back to the exam. And here's a list of some of the enzymes that are involved in protection. Dr. Weinberg, who hasn't taught in this class yet, but will be shortly, his whole career has been about something called antimicrobial peptides. I'd be shocked if he doesn't spend a lot of time teaching you about antimicrobial peptides, because that's his shtick. And some of the molecules on this list, defensins, for instance, cofacidin, S100, depending on who you ask, are these antimicrobial peptides. So we make, the equivalent to this is we make antibiotics. Antibiotics are things that kill bugs, right? We make enzymes or proteins that kill bugs. So we make our own endogenous, if you will, antibiotics. And I'm sure, I'd be shocked if Dr. Weinberg doesn't spend more time than one would expect from that. So since we're talking about the two big toes, here's an example of the rusty nail going through the big toe, the left big toe, but all that we're going to talk about for the next half hour is also true for the bowling ball. Let me check something. Yes. Okay, this is where I want to be. Okay. I want you to, we're going to wipe the slate clean for a moment, and you're going to design the next hour's response for those two big toes for me. So think a moment. You've got one toe where you stepped on a rusty nail, second toe where you crushed some tissue with the bowling ball. What is the first thing you would build into the response? What would be the first response you would like to see?
Which toe?
Well, did we talk about the, I thought we took about in this class that was the response for the first couple of hours and the two toes the same?
Yeah.
It ends up it's the same, so it doesn't matter which toe. So what would be the first response you'd like to build into the system? How would you protect us from the damage and the potential infection due to the rest of the yeah?
It's a sensory that something bad has happened.
Excuse me?
Sensory signal.
Perfect. That is, I've asked this question a couple times in various classes that I teach. This is the first time I've ever gotten that answer, which is the correct answer first. It's marvelous. The first thing you got to do is cry for help. The first thing has a sensory, you didn't say this, but I'm going to assume some of the cement is still in my throat. Yeah. I really don't like that. It's just you are great people and I'll do anything to help your career, but I really don't let go. And by the way, my dentist is actually a close friend, and I tell him just that. Today I told him I'm going to go to the dentist down the street from him because I can't stand being tortured by him. I think it was quite so bad. What was I talking about? Oh, cry for help. Okay, it's a cry for help. That sort of makes sense. Now, this is a tougher question. What is the first cell, or, I gave it away. No, too late. What is the first, yeah, well, it's too late. What is the first cell that you would have that would cry for help?
Is it the...
I'm just going to warn you, you're going to get it wrong.
Is it the Meissner corpuscle?
I'm sorry?
Is it Meissner's corpuscle?
I'm not looking for a name of a cell, I'm looking for a concept. Oh, but what did you say? I'm sorry.
I was thinking pressure receptor, but...
Pressure receptor. Yeah, that wouldn't be the first cell. Yes?
The cell that got hurt.
Cell that got hurt. Okay, the damaged cell.
Yeah.
Okay. That is usually the answer I get. It's actually not the right answer because the right answer is something you wouldn't think of unless you guys are incredibly bright, which I bet you are. Sure.
I was going to say the cells near the cells that got damaged, because then they would sense the
Okay,
damage.
so you've got the rusty nail or the bowling ball hitting the tissue, damaging some cells. Then there's some cells in the periphery that are still healthy, that are not damaged. Good, good. So you guys just gave me answer 2 and answer 3. So you gave me the second cell to respond, which is the damaged cell. You gave me the third cell to respond, which is the peripheral cell that is not yet damaged, but hey, the house next door is on fire, I better call the fire department. My house is okay right now, but I better call the fire department nonetheless. The first cell, you haven't told me the first cell yet.
Is it the neuron in the brain or sending information to the brain?
Oh God, that's hours later. Your brain's pretty slow. Your brain is pretty slow in this kind of a response. Yeah.
I'll go out on a limb and say.
Go out really far. That's what I tell you. You're gonna go, huh?
When you step on something, usually you look at it to see what happens. So
That's great. I love it. I have to figure out. No, listen, no. But I have to figure out how to put that into the class. Maybe if you guys invite me back next year, you can warn the first year class and your second year students about me. But yeah, I gotta put that in something. That's a cool answer. But yeah.
Are we talking like only cells of the body, or could it be like an exogenous cell, like a bacteria?
No, we're talking about a human cell.
Okay.
Yeah.
What about like the endothelial cell of a blood vessel?
Oh, that's minutes to hours, but we'll get to that in class today. Last one, and then I'll tell you the results.
Is it the cell that's in there?
Is there?
Bacteria.
The sentinel cell?
Oh, the epithelial cell. Okay, you're close. But that, when you step on a rusty nail or drop the bowling ball, the epithelial cell, which are the cells that coat the cells of the skin. Epithelial cells are cells on the outside of anything. So a liver has epithelial cells too, because a liver still has to be contained by something. So any cell that's on the outside of something, not just the outside of the body, is an epithelial cell. And sure, they're going to be certainly damaged as in the case. The cell that screams first is the dead cell.
Is that different from
Excuse me?
Wait, dead cells?
The dead cell. The cell, a cell, when that punctured the skin, you killed some cells on the way in. When that bowling ball hit the big toe, cells died.
Is that different from the damaged cell?
Yeah, they're dead. Damaged cell is still, if a damaged cell can cry for help, then it's still alive. It has enough wherewithal to drop a dime. The dead cell is the first cell, and the reason for that is there was a cytokine. I assume this cytokine was covered. It was called interleukin-1. Was that one of the cytokines covered? I don't know how Dr. Jin taught the cytokine class. I don't know if he taught you a bunch of cytokines or taught you concepts. Bunch of cytokines? Yeah, I teach concepts. I never mention the name of cytokines except for 2 or 3. I mean, I teach immunology 101 on campus, and main campus, and I mention 3 cytokines the entire semester. Because what's the point of memorizing a number? It doesn't make any sense to me. But anyway, this one I will mention. There is a cytokine called, I can't write in this room. It's called interleukin-1 alpha. You don't have to write it down, I won't test you on it. Interleukin-1 alpha is made in a cell, and it is never secreted. So the body never sees it, which is fine. But guess what? When the cell dies, it just pops open and spills its guts, and then interleukin-1 alpha is released, and that's a signal that something went wrong. Because the body is never ever exposed to that molecule unless the cell pops open, and the cell is only going to pop open if something bad happened. So the first cell to call for help is the dead cell, then the damaged cell, and then the periphery cell. We'll talk about what that cry for help is. This is the whole process. We won't come back to the slide unless you want to. I just wanted to set up the first, when you drop a dime, call for help. You guys probably don't know what that means. You guys never saw a payphone in your life, probably. Anyway, drop a dime is from the 80s, probably like cop chose or something. When they're in that cry for help, interleukin-1 alpha, which is a cytokine, it's a protein, not a prostaglandin, is released, and then we have to talk about where it goes, and we'll get to that next. The next signal that things have gone south is the production of not only prostaglandins, but carboxyl and a number of other molecules. And the stack is wearing off. So it starts with, so there is a molecule called arachidonic acid, which is, well, there are phospholipids in the cell membrane. Phospholipids, when they're stripped of their lipid, when the phosphates are removed from the phospholipid, produces the base molecule is called arachidonic acid. We have a number of enzymes that process arachidonic acid, as shown here, and you get a product of molecules shown here. I'm not showing you chemical structure, because you don't need to know it. In my opinion, I won't ask chemical structures in the exam. You can always look up the structure. You mentioned prostaglandins. Well, has it come up in class before? So I don't want to.
I'm just vaguely,
Okay, it's
I'm
you.
a
It's not.
long-term chronic pain
Yeah.
sufferer, so I've dealt with those quite a few times.
I am too, after this morning. Okay, so everyone here has taken Motrin, Advil, ibuprofen. You all have taken it for inflammatory response. Guess what? They're called NSAIDs, which is on the center of the board, non-steroid anti-inflammatories. And guess what? NSAIDs hit an enzyme called cyclooxygenase 1 and cyclooxygenase 2, two isoforms, well, they're not isoforms, two gene products that mediate the same enzymatic reaction. And that enzymatic reaction, with a couple more steps, which aren't on here, leads to the production of prostaglandins. Prostaglandins are that cry for help. The cry for help is going to lead to an inflammatory response. That's our goal here, to create inflammation. Well, you take anti-inflammatories because you've decided inflammation is a bad thing. The reason you take non-steroid anti-inflammatories, Advil, Motrin, and so on, is to block those two enzymes, and therefore block the production of prostaglandins, and therefore block one of the mechanisms of the cry for help. Now you can't block the IL-1 alpha from a dead cell because you can't control its cell dying unless you can reverse time. You got Superman to go around the Earth the wrong way or something, reverse time. One pharmacological approach is to inhibit the enzyme called cyclooxygenase 1 and 2 that lead to prostaglandin, which is part of the cry for help, which leads to an inflammatory response. Hence, that's why Motrin is anti-inflammatory. Okay. You see the next slide. So everything on this slide I've already said, and since I came late, I won't spend time on it. Or now, I'm not going to do this. I'll leave the refresher up there, we'll come back to that. Okay, this cry for help. What's the next step? Well, remember, we're designing the inflammatory response together. Where do you want these? Oh, okay, I didn't tell you this. So the prostaglandins will come from the damaged cells. And that's not surprising. The damaged cells have been damaged. Their membrane is already somewhat damaged, less than ideal. I drew a blank on the word I was looking for. And therefore, to break the membrane down, the phospholipids in the membrane down into arachidonic acid, ultimately prostaglandins, sort of makes sense. Then you've got the peripheral cells that are not damaged, but their next door neighbor ain't doing so well. They produce a bunch of cytokines. I'll give you the names of the cytokines because it sounds like you've got numbers. Don't write them down for me. I won't write I will never ask a cytokine number question, but you can write them down because maybe Dr. Jin mentioned it. But the cytokines that are released are TNF alpha, IL-1 beta, Remember, IL-1 alpha is never released until you die, or the cell dies. IL-1 beta is released as a cry for help from the peripheral cells that are next to the damaged cells, and IL-6. Don't write them down for me, but if Dr. Jin covered them, then write them down for him. I don't think I even have them on a slide that I can recall. Okay, so you've got IL-1 alpha, IL-1 beta, IL-6, TNF, and prostaglandin being released. Who are they going to talk to? What is the next step in this cascade of building an inflammatory response and protecting you that we need? This is a hard question. I may have to give some hints if I get blank stare.
Can you ask the question again? I don't think I understood.
I'm sorry, who's speaking? Oh, yes.
Could you ask the question again? I don't think I understood what you're asking.
Can you help me? What was the question?
What's the next step in the inflammatory?
Oh, yeah, well, who is the next cell? In the cascade or that? Our goal is to clean up, our goal in the left foot is to repair the damage caused by the rusty nail and kill the bacteria that were on the nail. The goal in the right toe is to just get rid of dead cells and debris and bring the toe back to normal. So what is, in this cascade of events to accomplish that? Well, actually, let me make things clear for you. The end game here is, remember, the first cell into a site of inflammation is a neutrophil. I told you that a month ago, you may not remember it, so I apologize. So our end game here is to get neutrophils into the site of damage, to clean up the mess. So now we've released these 5 molecules that are a cry for help. Who are they crying to? Who are they calling? Who would you have them call? Excuse me? Macrophages and neutrophils. Those are phagocytic cells. Neutrophils come in first, macrophages come in second. They take some time. Okay, where, I'm going to pick on you a little, don't take it personally. Where are the neutrophils?
Where are they?
When you're healthy, where are they?
In the blood.
In the blood. Right. So, I like it now. I'm trying to, on the spot, come up with an analogy. Okay, so the neutrophil that is in your big toe, right now when you drop that bowling ball, that neutrophil, those 1,000 neutrophils that are in the blood and your big toe, right then when you drop the bowling ball, they're in your arm, in your knee, in your hip, in your brain 5 seconds later. They're in the blood running around really, really fast. So how do you get their attention? We have to get their attention, so we can't just... So imagine these 5 molecules that I say are the communication tools. Where do they, if they're going to talk to the neutrophil, I'll pick on someone else. If they're going to talk to the neutrophil, where do they have to be when they're talking to the neutrophil? Blank stare, so that question didn't go over well.
No, the neutrophil
Where's the
is
neutrophil?
chemotaxic, right?
It's in the blood. So where do the molecules that are going to talk to the neutrophil and say we need help need to be? Right. 5 seconds later, where are they? Are they in the big toe? They're talking to the neutrophil when the neutrophil is in your elbow. Because the molecules, the 5 molecules are being swept away by the blood just like the neutrophils are being swept away. So we can't put those 5 cries for help into the blood because they won't be in the big toe long enough to accomplish anything. Does that make sense, everyone? This is very important because please, if someone doesn't get it, don't be shy. If we just release these molecules, these cries for help into the blood, they have lost connection to the big toe. They're just floating around. And the neutrophils, when they talk to those molecules, if they were the target, wouldn't know which organ was sick. Okay. So, with that hint, what would the cell you would talk to next be?
Maybe a mast cell?
Excuse me?
Maybe like a mast cell for inflammation?
Yeah, mast cells. Your mast cells are actually not involved in standard inflammation. They're involved in allergic and parasitic inflammatory responses, so they would, and their granules wouldn't help that much. What they do,
Is the answer any sort of inflammatory cell to recruit more blood to the area?
okay, get more blood to the area. That is one thing you want to accomplish, yes. Okay. How do you get more blood to an area?
Vasodilation.
I'm sorry, who spoke?
A number of us said
Oh.
vasodilation.
Well, let's start with someone new.
They said vasodilation.
Oh, you didn't say.
Vasodilation cells.
Who said it? Yeah, don't be shy. Remember, I'm deaf in one ear, so I can't locate where you guys are, so just wait at me. Vasodilation is the answer. Absolutely. And we'll get to that in the next slide. Okay, what controls the vasculature? What cell type controls the vasculature? You may not know it, but okay. A cell, the cell type that controls the vasculature is called an endothelial cell. Those are the cells, you got it? Good job. Those are the cells that face, come on guys, I'm here to have fun, just hopefully you will too. And maybe learn something. Those cells face the bloodstream. So, another analogy, I hope this works, is neutrophils are in the bloodstream just floating, running around real quick. Get on highway, I don't know if you've ever driven to I guess Toledo is acceptable too, but if you've ever driven to Chicago, which is probably nicer than Toledo, I know it's nicer than Toledo. If you've ever driven to Chicago, you get on Highway 80 or 90, I can't remember the number, I think it's both, actually, and you're on the highway. If you stay on the highway as you're driving into Chicago, do you ever get to see Chicago?
No.
You've got to get off the highway to enjoy Chicago. Neutrophils in the bloodstream have to get out of the bloodstream into the tissue to do their job. How do you know when you're on the highway to get off the highway?
Signs. Exit signs.
Exit sign. That was a hint. Now we're back to those 5 cries for help, talking to endothelial cells, exit signs, bloodstream, highways. Anyone? Anything clicking for anyone? If not, I did a shitty job. That's on tape, right? Good job.
The ABC.
Do like the endothelial cells have like tethering proteins?
They're called adhesion molecules, but yes. The endothelial cells in the big toe need to, you guys are doing great. What was that?
I said anything. I almost said a bad word.
You almost said a bad word, I've already said it twice. Endothelial cells need to put up an exit sign, just like Highway 80 or 90. You need to put up an exit sign so you know to get off. In Chicago, the endothelial cells have to look different. The surface of the endothelial cell facing the blood stream has to look different in the big toe than it does anywhere else. Does that make sense to everyone? So the target for your 5 cries for help is an endothelial cell, and what that endothelial cell does is it puts out adhesion molecules, which it normally doesn't express, and therefore when the neutrophil comes flying by, it goes, wait a minute, this is not good. They're asking for help. I need to do something. Okay. Go.
And that's different than the APC you talked about last
Yeah,
time?
this is all innate immunity. We haven't gotten a helpful cell into this tissue yet. We're still minutes to seconds after the damage. Okay. Do I do that now? Let's do this now. Okay, back in Roman times, these are Latin words. These are 5 Latin words. 4 of them are actually by Celsus. The last one means loss of function, so we're not going to deal with it. But these are the 5 landmarks of inflammation. You've all experienced it. This is not new. So you're going to tell me, if you know Latin, great, I'll translate to English if you need help. You're going to tell me why each of these 4 happen in an inflammatory site. First one is rhubarb. Anyone know what rhubarb is?
Rest.
Red. Okay, why is there redness at a site of inflammation? Who, you know the answer, you gave me the answer.
Vasodilation.
Right, vasodilation. Vasodilation, the vessels fatten, good scientific term, and therefore there's more blood per cubic millimeter than there was earlier. Therefore there's redness. Calor, heat. Why would a site of inflammation be hot?
They use energy and then,
Who's speaking?
I think they use energy and then
I'm sorry?
they use energy to do that.
They use energy, but they is vague.
Yes,
So I'll give you a hint. You're very, very close. What's the end game here? Well, yeah, the real end game is get rid of the crap, but how do we get rid of the crap?
Oh, to
Get the,
express those things at the end.
well, that's a step toward the end game. The end game is, as you said, what did you say?
You gotta call the ambulance to the site.
Right, the end game is to get the neutrophils inside into the site so they can clean things up. Well, guess what? That big toe has more neutrophils in it than it had when it was healthy, and those neutrophils are active and angry doing their job. Well, they need energy to do their job, and then when they make energy, when a human cell makes energy, it creates heat. So the hotness, or calor, at a site of inflammation is due to the fact you packed it with more cells that are more active, and therefore you're generating heat. Two more.
Swelling,
Excuse me?
hardness, swelling or
Hardness. Swelling and hardness. Why? What is a source of swelling and hardness? Why do you have it?
More stuff in the same area?
Excuse me?
Same amount of area, but a greater amount of things in it.
Things. Not scientific.
Neutrophils, blood.
Okay.
cytokines.
So there are two things, using your term, in the big toe that weren't there when you're healthy. One, more cells, because you packed it full of neutrophils to clean up the mess. And you did mention liquid. Why suddenly is there more liquid at a site of inflammation? Yeah.
From like diapedesis, so like just blood flowing, like leaving the blood vessels.
Okay, good. What's that called? What's the fancy word for that?
Diapedesis.
Hmm?
Diapedesis.
Diapedesis is, we'll get to that, is when the neutrophil crawls through the endothelial cell to get to the other side is the process of diapedesis. But what's the word for, I can't say it without giving it away.
Is it perfusion?
No, perfusion is an act of a clinician. We perfuse things.
Is that extravasation?
Extravasation and diapedesis are interchangeable. Extravasation means climbing through the vasculature. Diapedesis means changing shape to climb through the vasculature. Why would there be an increase in liquid? It's called swelling.
Increased permeability.
Right, vascular permeability. You know my next question. Why do we have vascular permeability at sites of inflammation?
It's easier for the neutrophils to go around.
Bingo. We've got to get the neutrophils to go through extravasation, or neutrophils to undergo the process of diapedesis to climb through. Well, if we make the blood vessels a little bit more permeable, climbing through a tight junction, the truly tight junctions, is going to be easier for the inflammatory cells if there's more vascular permeability. And Dover is pain, and pain is a product of possibility. Okay, so now what we have here is the endothelial cell. We just decided that the endothelial cell in the big toe, so here's tissue, so here's blood, here's an endothelial cell, and here's the tissue, and somewhere you damage. You release these 5 signals, cries for help. They go to the endothelial cell, and we decide the endothelial cell has to put out some kind of tether to say, hey, I'm different in the big toe than I am anywhere else. Okay? Excellent. What does the neutrophil have to have for this to work? Someone new.
I have a question.
Excuse me? Oh, no, I asked for someone new. just to liven up the group. I'm not even opposed to calling on you guys as a way of keeping you all engaged.
He said he has a question.
Oh, you had a question? I'm sorry. Thank you.
So, is this effectively like Velcro, like the cells put out this sort of like a loop, and then you would have these hooks that you roll along with?
Yeah, we're gonna get to the biochemistry right in a moment. Yep. But what does the neutrophil have to have? So we decided, thank you, Kevin, what he says. We decided the neutrophil has to put out a tether. We'll define the word better in a moment. Tether is not the scientific term. What does the neutrophil have to have to for this process to continue?
Slow down.
Just, I'm sorry? Who's talking? Who just spoke?
Elizabeth.
Oh, someone new also.
How about recognition?
Right. The neutrophil, the endothelial cell puts out this tether. I'll change the term in a moment. The neutrophil has to know that tether's there. The neutrophil needs a protein or a molecule. Let me not say protein. Be very careful here. The neutrophil needs a molecule to recognize the tether, to know that there's a cry for help associated with the event. Okay? Now, there are many biological processes, but the two we're going to focus on right now are induced and constitutive. A molecule can be induced, meaning it's not there, and then suddenly something happens and it gets expressed. Or constitutive, it's always expressed. We've got this tether on the endothelial cell, we haven't changed its name yet, and we've got a recognition molecule on the neutrophil. So the neutrophil can see the tether. Well, do you want these two molecules both induced, both constitutive, well, both induced, that's induction, both constitutive, meaning they're there all the time, one induced, one constitutive, or one the other way? So we'll just take a vote in the class. How many people think you want them both constitutive? No one. Great, because if you're both constitutive, then the neutrophil is climbing out of the blood vessel all the time, and you're one big bag of inflammation. You don't want them constitutive. How many people want them induced on both? We've got two cells. We're only interested in two cells here. The endothelial cell and the neutrophil. Do you want them both induced on the two cell types? How many folks want them both induced? Looks like 4 or 5 of you, a minority. How many people want one induced, one constitutive? Excellent. That is the right answer. For anyone who raised their hand for induced and constitutive, why? Which one's induced? We already know, I told you. The tether is induced by the 5 signals. We know that. Why do you want the recognition molecule from the neutrophil to be constitutive? Yeah.
Because it's always readily available to
Right.
recognize.
Faster the better. We're looking for a fast response. If the neutrophil has a constitutive and the endothelial cell throughout the body, a healthy body, never has the tether, we're cool. Nothing bad happens. The moment the tether comes out, the neutrophil will recognize it, bingo, we can start the process. Induced, constitutive. Everyone got that? Excellent. Now, next challenge along the way. And help me, this analogy I've used a couple times. I don't like it. If you can come up with a better analogy, tell me. But imagine you're on a Delbert. There's a bicycle race, it's not winter. It's beautiful May day, it's a bicycle race on a Delbert. There's a bike going down a Delbert, and people lining a Delbert on both sides. Bicyclists go, I think, 30 miles, 35 miles an hour when they're really going, I think. Okay, imagine if you're a spectator and you reach out and grab the arm of a bicyclist going by at 35 miles an hour. What do you think will likely happen to the spectator and the bicyclist? That's a bad thing. Most likely the bicyclist's arm will pull out of their shoulder and the spectator's arm. If the grip is unbreakable, the spectator's shoulder, the arm will pull out of the shoulder, and the bicyclist's arm will pull out of the shoulder. That's what we've got right there in the neutrophil. The neutrophil is going by at the speed of blood. which is pretty fast, and you could ask me the number, and I don't know the number. I should know it, but it's pretty fast. So we can't have the tether and the recognition for the tether be a very firm adhesion. If it were the spectator grabbing the bicyclist's arm and not letting go no matter what, both cells, both people get damaged. If the tether and the recognition molecule in the neutrophil formed a tight bond, it was unbreakable, both cells would be ripped apart. So we can't do that. So what we do, or what God did, I guess, is she made the first interaction, this rolling interaction, to be what's called a weak interaction. Scientifically, low affinity. Let's see if the next slide has it. Oh, there's a picture of those are T cells, actually. Oh, wow. T cells adherent to the endothelial cells. But the low affinity interaction involves a molecule called a selectin and a carbohydrate. So there is a low affinity interaction such that, now imagine that bicycle analogy, where you grab the bicyclist and let go almost immediately. That bicyclist is going to slow down just a tad. 5 people down, 5 people to your right, assuming they're going this way. 5 people to your right grabs the same bicyclist, they're going to slow down a little more. Let's go. Another 3 or 4 people. You grab the bicyclist, slows them down. Slows them down. Every person grab and let go, grab and let go. Slowly you are going to, not slowly. In the long run, you are going to slow that bicyclist down. That's what's happening with the endothelial cell and the neutrophil in this step called rolling. It's a weak adhesion, strong enough that they interact, weak enough such that they let go so no one gets killed. Neither cell gets killed. And you do this along the way. It's called rolling in the literature. I actually think of it as jumping, because when they interact and there's this weak interaction and then they let go, this cell is still being swept away by the blood vessel, and it doesn't go to the very next endothelial cell. It goes 10, 20, 30 cells down. But rolling is how it's taught, so I'll just tell you my bias about jumping. So a series of weak interactions to slow the neutrophil down and to deal with the blood flow, the reduce the pull of the blood flow. Yes, sir.
These neutrophils are going along to the lumen of the blood vessel there.
True.
But that one should like to think that's more or less in the center of the lumen. How do they get to do they reach out and get grabbed?
Perfect. You just answered, you just asked the question of a topic I was about to cover. Which is bigger, a neutrophil or a red blood cell? Neutrophil. So because neutrophils are bigger, and don't ask me why, I should know this, and I'll have to look it up. Bigger cells tend to go more to the periphery than the smaller cells.
Oh,
I
be
don't,
centrifugal force, I guess.
yeah, I'm sure it's something like that, but I need to look it up. The other thing is, remember we built in vasodilation? There's vasodilation going on. I don't know if any of you have canoed or been to small streams, but imagine if any of you have canoed or streamed, been in smaller streams around the world. When the stream, when the bedside of the stream is narrow, the water is going fast. Then suddenly the bed gets bigger, which is vasodilation. And you have this little pool where you can swim, and the water slows down. It's exactly what's happening in the blood vessel. Vascular dilation leads to a slower flow of liquid through that area. So you've got neutrophils that go to the outside because they go to the outside, and now they're going slower anyway because of the vascular dilation, vasodilation. Does that make sense to everyone? Then you've got these arms reaching out and grabbing a little bit and letting go, a little bit and letting go, a little bit and letting go. That's rolling. At some point, the neutrophil is going slow enough that you can kick in a strong interaction, which is mediated by these two molecules. And now that strong interaction is high affinity, which means the neutrophil stops. which is activation. I'm sorry, activation. Well, it's not really activation. Activation occurs after arrest. I just realized this slide's wrong. Arrest is the next event. Now, why do we want the neutrophil stopped? Why can't it just sort of be rolling? What's our end game again? The neutrophil has to squeeze between. Look at the size of the neutrophil, and it's got to squeeze between these two cells. The neutrophil has to go through a process of diaphoresis, which is the breakdown of its actin filaments, for it to squeeze. You don't want the cell flapping around. You want that cell firmly adhering right here, so that all those processes of changing its cytoskeleton so it can squeeze through can occur. So you need that high affinity interaction next. And that's mediated by cell adhesion molecules and integrins. Same question. Do you want both of those molecules to be constitutive? Do you want both to be inducible? If you want one constitutive and one inducible, what cell do you want to be inducible? So how many folks want both those molecules for high affinity to be constitutive? No one. Excellent. How many want both of them to be inducible? No one. Excellent. Where we want to be. Perfect. One's inducible, one's constitutive. Which one? Think a minute. Any guesses? Okay, then let's just think about. Oh, yes, please.
Is the integrin inducible?
Yes, so there's a vote for the integrin being inducible. How many folks agree with that? Less than half. So most of you believe that the cell adhesion molecule should be inducible. Is that yes? So most of you are not voting. Remember the deal we made a month ago? That I would try my best to keep this as entertaining and educational as humanly possible if you guys played my game. And part of my game was to vote. So there were 70 in your class, the 50 of you who didn't vote, you're not keeping up your end of the bargain, guys. Yeah.
So in the rolling stage, you said neutrophils were constitutive, and then the epithelial cells were induced.
Endothelial cells.
Endothelial cells. Why would that be different in this step?
I didn't say what. I'm just asking.
Oh.
Which would you do? How would you design it so that? How would you design it? So there was one vote for inducing the integrin, which is on the neutrophil. So come on, guys, keep the promise, or I'll just start going through PowerPoints and be boring. I don't know if I can do that, but I'll try. How many people think the integrin is an inducible molecule? Looks like the majority. How many people think the host cell adhesion molecule is inducible? Okay, so it's about 40, 60, and the integrin is inducible. Why? Could the cell adhesion molecule be inducible and the integrin be constitutive? Yes, it would work that way. So I don't have a great answer on the why there, but I can tell you another step that's on this slide that we haven't talked about yet. So now that I've given you a really lousy answer on why it's the integrin that's inducible, since I don't have a great answer. How would you design the induction? What property of inducibility would you build into the system?
Maybe when it's going slow enough?
Excuse me?
Maybe when it's going slow enough?
Well, when it's stopped. So yes, one thing we're going to build into the system, well, it can't be stopped. It's got to be inducible when it's going slow enough, you're right. The high affinity causes it to stop. So I don't know what I was talking about. So the neutrophil has had to have slowed a great deal for this induction to occur. That's one thing. What other feature of the inducibility would you want?
Like a single transduction pathway to cause the receptor.
A signal transduction pathway and response to a receptor. Okay, for those of you, yes, sir.
I was gonna say, kind of like how enzymes work, like attaching and and then kind of changing
Changing.
form to make it functional.
Okay, so those are two different things. You're talking about a structural change.
Yeah.
You're talking about a receptor-mediated event that leads to the induction. What's our goal here from a, okay, where did we do this? I can't remember now. I am drawing blank on when I said this already in the hour. So I'm going to give this to you because one, it's 2:10 and you probably need a break soon. We want the induction to be incredibly quick. We talked about fast earlier, and I can't remember what we were talking about, what event we were talking about, we want really fast, but we want the induction to be fast. You've got structural change in integrins versus signal transduction, receptor-mediated signal transduction, which is faster? Sorry? The choices, I forgot your name?
Mina.
Vina?
Mina.
Vina.
That's right.
And
Austin.
Austin. So Vina said a structural change in the integrin to allow for this adhesion to occur, tight adhesion, high affinity adhesion, or Austin said signal transduction, meaning a receptor-mediated event that leads to a change in cell function. Which is faster?
Signal transduction.
Right. So it ends up, the integrins sit on the surface, and literally they look like this, in a resting cell. And those are called inactive integrins. And with a response to a signal, we still have to signal to the neutrophil, and we'll get to that in about 1 minute, and then we'll take a break. The integrins look like this, they're more like that in the picture. So integrins go from a crossed, flappy, bent-over structure to a straight, parallel structure, and when they reach that parallel structure, that's when they're active. They can bind to cell adhesion molecules. They can bind in this conformation, they cannot bind in this conformation. That's a rather rapid event, and we want speed here. Okay, but what we need then is a signal to the neutrophil to do that. The neutrophil can't just, I guess theoretically, this interaction, the low affinity interaction that I talked about, could be a signal to the neutrophil to make an active structure to the integrin. That could be a method. It is not the one chosen. It ends up that these endothelial cells also express chemokines. Did Dr. Jin talk about chemokines at all? Okay. I will not mention names again, but if you need to memorize names for him, that's what he's for. So it ends up the endothelial cells will make chemokines. And these chemokines will activate the neutrophil to lead to that structural change in the integrin so that it can be a high affinity binding molecule. Tight interaction. Strong interaction. Yeah.
Are those chemokines released when it starts rolling, or is it later in the process?
Perfect. That's where I was going to end this hour. When are the chemokines expressed? What would be the signal for the chemokines to be expressed? Oh, come on, you know this. What's the signal for the selectin? We decided selectins are induced, right? To start the process.
Cellular trauma?
So, yeah, the same 5 cries for help that we started this hour with, those cries for help interact through receptors on the basolateral surface of the endothelial cells, activate the endothelial cells to make the selectin, to put out the tether. They also activate the endothelial cells to synthesize the chemokine, so the chemokine is there, ready to activate the neutrophil. Okay, one small problem. What happens to that chemokine after it's released by the endothelial cell? Remember, cytokines, Dr. Jin said this, cytokines are secreted molecules, mostly, a couple of exceptions. Cytokines are secreted molecules. So the chemokine is going to be secreted by the endothelial cells. What's going to happen to that chemokine? Where's that chemokine going to be 5 milliseconds after it's released?
In the bloodstream,
In the bloodstream. Where's it going to be in the bloodstream?
far away.
Far away. It's going to be swept away. So the chemokines can't just be released. If they are spit out by the endothelial cell, they're going to be swept away by the blood. So the ends up, the chemokines, it's not on this slide. I don't think I have a picture of it. I don't have a picture. But it ends up, the chemokines bind to a cell surface, lectin, a heavy carbohydrate modified protein that holds the chemokine in place and sort of presents it as on a gold platter to the neutrophil. So the neutrophil's receptor can interact with the chemokine and activate the integrin for strong adhesion. After strong adhesion occurs, then the neutrophil can crawl between the endothelial cells through a process called diaperesis or extravasation, and clearly the neutrophil has got to change its shape in order to do that. All right, see you guys in 7 minutes. How's that? Climbed out of the vessel, they're in the tissue, they are phagocytic, they destroy things. One step we have not included yet is how did the damaged cells, remember think of a core, apple core, avocado pit, yeah, avocado. The dead cells of the pit, the damaged cells are the meat of the avocado and the skin of the healthy cells. Think of that scenario that you can. How do those cells know that something went wrong? We need to add a step to this, which is a signal to them to cry for help. We started with the cry for help. We now need to add now what is the signal needed for help. And now we're going to start to separate the two big toes, because there are going to be infectious agents in one big toe and no infectious agents in the other. Okay. Did I, again, I apologize, a month ago, I usually don't forget what I teach, but it was a month in between classes. It's absurd, in my opinion. Did I talk about specificity at all? Did I talk about big patterns versus very discrete recognition with you guys? Just shake your head yes or no. Most of you are saying no. Okay. If I go outside and I see this metal object with 4 tires on it, and then I see another one, another one, another one rolling by, what am I going to call that? Cars. That's a pattern. It could be a Hyundai, it could be a Toyota, it could be a Lexus, it could be a Chevy, it could be a Dodge, if they still make Dodges. But they're all cars. So when I talk about pattern recognition receptors behind me, a car is a pattern. These are seats or chairs. The chair you sit on at home when you watch TV is different from the chair that you sit on at your desk. It's different from the chair at these movie theaters that roll back and stuff. But they're all chairs. So chair is a pattern. Car is a pattern. The specificity of the adaptive response, just to give you a hint of where we're going, is imagine the shape of the button that turns on the radio in a Lexus versus the shape of the button that turns on the radio in a Chevy. An antibody can tell the difference. So the antibody is highly specific and can tell the on-off button of a Lexus from the on-off button in a Chevrolet. That's specificity. Pattern is a car is a car is a car. Okay. So the innate response relies on patterns. The adaptive response relies on specificity, which we'll get to in about 5 or 6 sessions with you. Now we're only going to talk about patterns. So we have receptors. Everyone comfortable with what the word receptor means, what a receptor is for? Anyone uncomfortable with that? We good? Excellent. We have receptors that recognize patterns, and these patterns are distinct to infectious agents. So there are patterns that are on infectious agents, that chemical structures, if you will, that are on infectious agents that aren't on human cells. The easiest one for me to use as an example is the flagella. Bacteria have flagella. All bacteria have flagella. Human cells don't have flagella. So we have a receptor, a pattern recognition receptor, that recognizes flagella. Well, that pattern recognition receptor in the big toe binds to a flagella. It's going to tell the cell it's associated with, we've got a bacterial infection. There's your trigger for all the cascade we talked about for the first hour. Everyone got that? Anyone not get it?
Wait, say that one more time. The whole
Cells,
thing, just the key point.
excuse me?
Not the whole thing. but
No,
just
you're
the
not
key
gonna get the whole
point.
thing. I couldn't remember what it was. Cells throughout the body express pattern recognition receptors whose trigger is associated with infectious agents, not human cells. So if you get an infection, the pattern recognition receptor triggers, and that cell therefore knows something's wrong. Anything else on here? So, immune surveillance, I mean, what I just said, the fancy word for what I just said is immune surveillance. Different functions, it starts inflammatory responses, starts phagocytosis. Ultimately, remember, the end game is to get neutrophils in there to be phagocytic. So hence, triggering a pattern recognition receptor will ultimately lead to phagocytosis, antiviral responses. So, who are these pattern recognition receptors? Where are they first? Test question. They're expressed on the cell surface. That's the guy right here. They're expressed in the endosome. That's the guy right here. And they're expressed in the cytosol. That's the guy right there. That'll be an exam question, just that simple. I mean, that's the exam question. Name the three tissues, or I guess it's multiple guess, so I'll have to give you stupid answers, and the three that are right answers are those three. Why? Why put it on the cell surface?
With recognition.
Excuse me?
With recognition.
Right. I'm going to go a little short on time. The bacteria is outside the human cell before it's done anything bad. So you want things on the outside of human cells to recognize that there's bad guys around. So that falls into quick recognition. Cytosol is easier than endosome, so we'll do cytosol next. Why in the cytosol? Right, do bacteria usually enter human cells? In general, if I gave you 100 bacteria, would you say 90 of them enter or 90 of them don't enter?
Don't.
Bacteria usually don't enter human cells. There are certain ones that do. Tuberculosis can enter human cells, but in general, bacteria don't enter the host. Well, what infectious agent does enter the host? Viruses. So in general, most of the cytosol detecting agents are viral. Not all. Some bacteria do enter the host. Why the endosome? And notice, I want you to be careful here. The recognition part, meaning the part of the pattern recognition receptor that binds to the infectious agent, is the hook. This is the recognition part. So there's something inside the cell too, we'll get to that in a moment, but the recognition part is outside the cell, the recognition part is in the cytosol, the recognition part is in the lumen of the endosome. Why do we put them in the endosome?
Because it keeps it sequestered from the cell contents.
For RNA.
But remember, their goal is to recognize things. Their goal is to trigger us that bad things, bad guys are around.
Retroviruses?
Excuse me?
Retroviruses?
No. I can define what retrovirus for you later, but no. So remember, what's going on during the inflammatory response? Phagocytosis. There's a huge amount. Remember the dendritic cells. Remember I did about gulping and drinking and all that stuff? Gulping, sipping, and drinking. Sipping, drinking, and gulping. These cells are bringing in extracellular fluid all the time. They bring them in to endosomes. So if they happen to drink in a bacteria of some kind, or a virus, or fungus, or whatever, you want some surveillance going on in the endosome itself. Just in case you missed it on the cell surface, if the cell endocytosed liquid and brought in an infectious agent, you want to be able to detect that infectious agent while it's in the endosome, and then, of course, in the cytosol, mostly for viruses. So those are the three locations you put pattern recognition receptors. And the next slide, don't have to memorize this, but just to get a feel for cell wall. We don't have cell walls. Bacteria do. Therefore, a cell wall is going to be a target for a pattern recognition receptor. PAMP and DAMP stands for pathogen-associated molecular pattern. The key word there is pattern, not the PAMP part. And DAMP stands for damage-associated molecular pattern. Again, one big toe, we need to get things angry. When you step on the rusty nail, the other big toe, we damage the cells, we didn't infect them. We need to get those cells angry too. So we have PAMPs, which are associated with the bug, and DAMPs, which are parts of the human body that are normally not exposed. And when they are exposed, it's a signal that something went south. So bacteria have cell walls, we don't, therefore we have pattern recognition receptors for cell wall. Bacteria have flagellas not on here. Bacteria have flagella. Therefore we have a pattern recognition for, oh, here's flagella. It ends up that the DNA sequence CG in humans is methylated. Bacteria don't methylate the G in CG. So therefore we have a receptor that recognizes unmethylated CpG, which humans don't usually have. So if there's DNA that has a CG sequence with G unmethylated, that came from a infectious agent. That's how these trigger. That's how infectious agents trigger these pattern recognition receptors. Damage-associated molecular patterns. Crystals, this is associated with disease. What's the disease where you get crystals in your foot and you... Gout, thank you. Crystals form from gout. Actually, crystals form from myocardial infarction as well. Heat shock proteins. Heat shock proteins are only expressed when the cell is damaged. So each of these, if you go through them all, are damage-associated responses, and we have receptors that recognize proteins that say we've got a damaged cell, we need to start the process. So these are receptors. Receptors have two jobs. One job is to recognize whatever it's supposed to recognize. In this case, patterns of infectious agents or patterns of damaged proteins, or proteins due to damage. Once you've recognized, once that ligand has bound to the receptor then has to talk to the inside of the cell and tell the cell something happened. So this receptor, all of these receptors, have two parts. The parts that recognize the infectious agent or the damage, or the components of damage, and then another part that starts a signal, going to Austin's comment, it starts a signal transduction process to start the cascade we just talked about. So there are, I don't know if I want to do this in detail. One of the pattern recognition receptors are called toll-like receptors, and there are 9 of them, there are 11 of them, depending on who's counting or carrying them in, and they each recognize as listed here various components. And notice that they all have a recognition part and a signaling part. The signaling part is very, very similar, because once you recognize an organism, you want the cell to be angry, and you don't need to tell it to be angry 9 different ways. You can tell it to be angry one way, once you've recognized the infectious agent. This is a repeat. It shows you the various, various ligands that bind to target receptors. Notice the number of changes and the organisms that express it. And then I want to introduce, I guess it's the next one, 3 other. So there are 4 families of pattern recognition receptors. I just talked about toll-like receptors. The second family are CLRs, which are cell lectin receptors. So there are certain sugars that bacteria make that we don't make. A lectin is a protein that binds to sugars, period. A lectin, by definition, is a protein that binds to sugars. We have lectins that only bind to sugars made by bacteria. Therefore, it's a trigger to tell the cell there's some bacteria around. The third, so toll-like receptors, cellular lectin receptors. The third one is RLR, and that's, maybe I have a better slide, because it's not as easy to remember why. Let's go to RLRs first. Okay, so it ends up that RLRs are called RLR because the very first one found was RIG-I, RIG-1, depends on who you ask. And RLR stands for Rig-like receptor. Since we found Rig, we thought there was only one, we called it Rig, and then suddenly we found the whole family. So these are receptors that are cytosolic, and they are for recognizing unique nucleic acid structures associated with viruses. So we cap our RNAs, viruses cap their RNAs a different way, enzymatically different, leading to a different chemical structure at the 5' end. We have receptors called of the RLR family that recognize the viral cap from the human cap. And the fourth molecule that I want you to recognize is an NLR. And again, N comes from the fact that the very first molecule we found was called NOD. We have to write that down. But once we found NOD was really a part of a big family, we call them NOD-like receptors. Just like RIG-I is Rig-like receptors, NOD is NOD-like receptors. That's NLR, RLR. And CLR, L is lectin. That's the key word to remember that. NOD receptors are present in the cytosol. And NOD-like receptors are present in the cytosol, and there are a whole family of them is shown here. You don't have to memorize what the families are. But they initiate cytosolic signaling differently than all of the various other receptors I've talked about. All the other receptors initiate a signal transduction pathway, and if anyone is uncomfortable with what signal transduction is, we can talk offline about, describe signal transduction too. The NLRs initiate a process that involves a very complex structure called the inflammasome. That's amazing. Huh. That's awful. So I don't have the word inflammasome anywhere here. That is just awful. My fault. Anyway, that very large structure that we're staring at there is an inflammasome. It's a multi-component molecule, enzyme really. It's really an enzyme. that has the capability of recognizing infectious agents have entered the cytosol, and then its main goal is IL-1 beta, the molecule we talked about last hour, is made as a 35 kilodalton protein when it's synthesized from its gene. That 35 kilodalton protein sits in the cytosol inactive. It is cleaved by the inflammasome, as you'll notice right here. This should be a beta, to be correct. The 35 kilodalton IL-1 beta that sits in the cytosol and doesn't do anything is cleaved by the inflammasome to a 17 kilodalton molecule called IL-1 beta that is released by the cell. And remember the 5 signals, the cries, 5 cries for help? One of those cries for help was a release of IL-1 beta. So IL-1 beta is released by these cells in response to an inflammasome taking the full-length molecule, cleaving it in half, about half, and then releasing it. And don't worry about IL-18. Okay, good. As I mentioned, NORs, I'm going back here, I apologize. NORs go through the inflammasome, while toll-like receptors, lectin-like receptors, and RIG-I RLRs use signal transduction as their main mechanism to communicate with the cell, so that the cell is aware of a change in its biology such that it responds and sets everything else in motion. I'm not gonna worry about those. It's in your PowerPoint. By the way, guys, if you don't get this PowerPoint posted by tomorrow, call me or text me or write me or something, and I'll track it down with the dentistry folks. Okay. So where are we? So pattern recognition receptors fall. Remember the exam question? They're present on the plasma membrane. They're present in the endosome. And remember, they have to face the lumen of the endosome because that's where the organism will be. Or they're present in the cytosol because that is most likely where virus will be. And in general, the toll-like receptors are present. This is something you do want to remember. I didn't put TLR in red. Toll-like receptors are the molecules that are present on the plasma membrane and the endosome. The NLRs, that's the NOD family, NLR should have written. RIG family, RLR. These are present in the cytosol. RIG family goes through signal transduction. The RIG-I family goes through signal transduction. The NOD or NLR family goes through the inflammasome. This is part of the 5% rule, don't worry about it. I just mentioned signal transduction, just described the second bullet to you. The toll-like receptors go through signal transduction. RIG-I goes through signal transduction also, or RLRs. NLRs go through the inflammasome. Net effect is the release of cytokines. And in the case of innate immunity, that's IL-1 beta, IL-1 beta, IL-6, and TNF. 3 of the 5 cries for help we talked about last hour. Chemokines. We haven't talked about why we need chemokines. We'll do that right now. It initiates the arachidonic acid degradation pathway leading to prostaglandins. And antimicrobial peptides. I think I have one slide on it coming up. But again, I'm expecting that Dr. Weinberg will spend a lot of time on antimicrobial peptides since that's his research interest. Now, where do you want these molecules? So these are surveillance molecules. Where do you want them? Certainly want them on the epithelial cells, because those are the cells that are facing the outside world, and if something bad happens, you need to know. You want them on interstitial cells, cells of the big toe, resident cells in the big toe, because they are the ones that may get damaged, or they're going to be next to the damaged cell. and you want them on infiltrating leukocytes, that's mostly neutrophils and macrophages for innate immunity. Why? Because you want those cells angry and you want to stimulate them in many ways as possible and make sure they're fully activated. Okay, we haven't talked about, we talked about chemokine in one context, just to remind you. Endothelial cells express chemokines to activate the neutrophil when it's still in the blood, in the movement of the blood vessel. But what happens to that neutrophil once it climbs? Once it climbs through the endothelium, now it's in tissue. What do we want to do with that neutrophil next? Let's go with someone new.
I have a question.
Did you have a question? Yeah, I'll come back. Let's go to the answer first, then we'll come back to your question. So what do we want? The neutrophil is now in the tissue. What do we want to do with it next? Yeah. Oh, wait, now someone new. Just because I need to know, I don't care, I'm not judging you guys at all. Are there many of you silent because you're just not your thing to answer questions, or you just don't know the answer? How many of you just don't know the answer most of the time? Thank you. So for those of you who don't know the answer, I'm going to coach you through it, so you can give me the answer ultimately. Neutrophils are, so on this scale, the endothelial cell this big, the neutrophil this big. The big toe fills this building and the next building. Or maybe more, I'm not good with dimension. The big toe itself is enormous based on this scale. So the cells that got hit by the bowling ball, killed by the bowling ball, damaged by the bowling ball, or the rusty nail could have happened over in your dental building. Or might have even happened in Wall Street. That was a hint. Not a very good hint, obviously.
You need to direct the neutrophil to the site of damage.
Perfect. Okay. So, I think it was Hansel and Gretel. How did Hansel and Gretel find their way out of the woods?
Breadcrumbs.
You guys do know the answer. So now, what's the answer? What do chemokines do?
Chemotaxis.
Chemokines are the breadcrumbs to the site. Remember, we decided that chemokines, let's get our action over here. You guys know this. I want this to make sense rather than just stuff to memorize. These pattern recognition receptors are going to be triggered. They're going to be triggered at the site where the infectious agent is, or where the damps are. Those cells at the site of damage or injury are going to release chemokines. Now, using the breadcrumb analogy, how does a neutrophil, what's going to happen with those chemokines in order for the neutrophil and the breadcrumbs to all work together? Correct. Nothing? Let's try this. Where is the highest concentration of chemokines in the big toe? I'm sorry? At the site of injury. Because those are the cells that are making it. What will happen to the concentration of chemokines as you go away from the site of injury toward the blood vessels? There's going to be a gradient of chemokines, low in the blood vessels, high at the site of injury. Hansel and Gretel, breadcrumbs. The neutrophil will climb out of the blood vessel, follow that gradient to the source, and then start gobbling away. Phagocytosis. And repairing the site of injury. That is the other function of chemokines. Now, what did I mention to you? This is a harder question. what did I mention to you when we talked about chemokines in the endothelial cell and the bloodstream about if the endothelial cell releases the chemokine, it's going to float away with the blood. So the endothelial cell binds it, or attaches it to its surface. What's going to happen to this gradient over time? Is it going to be stable or is it going to be somewhat unstable? There's fluid. Remember, we just introduced vascular permeability. We introduced fluid. So there's a lot of fluid sloshing around. I'm going to save the time. Because we end at 10 up or on the hour?
Generally 10 up, but whatever
Okay,
time it takes.
well, I'll try to stop. Soon, very soon. Do you have a class at 3? Oh, then I'll definitely stop soon. Yeah, we've introduced fluid. Fluid's going to slosh around in the big toe. That gradient is going to be disrupted. But the neutrophil needs to follow that gradient to find the source of the damage, the source of injury. So chemokines have this property of binding to cell surface molecules. So that gradient is maintained because they're not floating in the interstitial fluid of the big toe. They are attached to cells along the way. Sure, they get into liquid a little bit, and that's how the gradient is established, but it's maintained from being very low at the blood vessel to higher and higher and higher. Anyway, the gradient is maintained because chemokines have this ability to bind to cells. So the gradient is maintained so that, using the Hansel-Garrow analogy, the neutrophils know where to go. And you both had a question. You had a question first.
Well, let us just suppose theoretically that there was some genetic problem and the neutrophils in an individual didn't express those inducible integrins.
It's called bald leukocyte syndrome.
Okay, so
There is a
could
human disease.
the neutrophils still get to the site at all, or
Yeah.
there just be less of them?
Yeah, the bald leukocyte disease, I don't know great details about it. Those people survive, but their infectious rate is higher and they're sicker their whole
So
life.
they still get in, just,
Yeah,
okay.
yeah, because what I didn't tell you is I talked about a selectin binding to a carbohydrate. There are PEN, yes? Maybe it's only P and E and N. Selectins. There are 3 different selectins, and there are lots of carbohydrates. So, we got some redundancy in the system.
Okay.
Yes?
How are chemokines released on the outside of the cell to trigger?
They're secreted, right?
Secreted, but then bound on the inside to maintain that gradient.
No, they have to be bound on the outside of the interstitial cells. Remember, the neutrophil has to crawl its way through the tissue, so the chemokines are on the outside of all the tissue cells, so they can find them.
Okay.
So the neutrophil can find them.
Okay.
Let me think. I think I will just stop here. Let me see if I have anything. I'll just end with a statement. You can look at the slides. I won't touch on all that stuff. No surprise. We have mechanisms to shut the innate immune response down because we don't want it to go on forever. And bacteria or infectious agents have mechanisms to fight the system so that it never gets kicked off in the first place. No surprise. We're in constant battle with our environment. Thanks for putting up with me. I'm sorry I was late. And I think I see you on Wednesday.
Thank you.